Hello.
Hello.
I'm the host now. All right. Doesn't look like I combed my hair this morning. Interesting. All right. Let me just make sure that I got things set up correctly. Sure. Pretty well. Yeah. So by the way, we're having Zoom tenure track job interviews every afternoon this week, in case you haven't heard, which probably you have. So it's every day at 4. So today is the first one. It's Yiming Zhao, who is in analysis/geometry. I guess I'll skip to the fact that the number theory candidate is Juya Wang. She's a student of Melanie Wood, really 2018 PhD. She was our top pick. She seems really, really strong. She works on kind of arithmetic statistics and several different things, but most of all, Mala's conjecture, counting number fields with specified Galois group by discriminant. So she has some breakthrough results on Mala's conjecture. This is just going to be what it is. Okay. Anyway, so yeah, so her talk is Thursday at 4. I'm super excited about the prospect of getting her at UGA. So please feel free. I mean, I'm sure it'll be an excellent talk. All right. Let's see. Are there any questions? No. Okay. So I think I would like to. I mean, look, we can't spend the entire course on chapter 1 of the textbook, unfortunately. So I'd like to get out of chapter 1, finish with chapter 1 today, even if we don't cover things in, full detail. It is a book you can go back and read. So yeah. So I think today is going to be a bit of this, a bit of that. After I guess there's a couple things that I still need to, couple things that I still owe you. So this is this, as I was telling you, this kind of benign result on the border of ring theory and homological algebra, which is this is kind of like the derived functor consequence of these like tensor and Hom identities, which I introduced last time. And so we use this theorem to prove the 3 versions of Shapiro's lemma. Right? And so, yeah, and so I'll go through the proofs are really so quick. There's no need to skip them. They're so quick. So for instance, for this one, we have a flat ring homomorphism, and then we're getting, let's see, yeah, so we're seeing that the Tor, let's see, M is an R module, M is a mod R, so M is a right R module, N is a left S module, just has to be that way. That's the way tensor products work in general for non-commutative rings. And then you get the Tor over R of M comma N is canonically isomorphic to the Tor over S of M tensor from R to S comma N. Right? And so we use that to prove the homological Shapiro lemma. Okay, so let's just see the proof of it is I mean, it just works basically. So yeah, so I'm trying to prove something about Tor. So I should be taking I get to compute a Tor functor. I can take a projective resolution of either argument, M or N. And so to prove this, I want to take a projective resolution of M in right R modules. Doesn't really matter, but that's the correct. Doesn't change anything really, but that's the correct thing. And okay, well, why did I assume that S was a flat R algebra? Well, if it's flat, then tensoring with S preserves exact sequences, and so therefore this resolution, which is an exact sequence, once I tensor it with something flat, is still a resolution. For anything, if you base change a projective, if anything is a projective R module, then that thing tensor S is a projective S module. There's no condition on R and S, that's always true. So we tensor our projective resolution, we get a projective resolution, and therefore we can use that projective resolution to compute the Tor over S of M tensor R of S. And so what does that mean? It means so then we tensor over S with N and take the homology, but now by our tensor-tensor identity, our telescoping tensor identity, this tensor S goes away. And so then I'm just, for some reason, I decided to go from right back to left. I don't really know why I did that, but if you go from here to here, then that's the same as the homology of this, but this is clearly what we need to take the homology of to compute the Tor of regular alt m into n, and that's a backwards check mark. I don't know why I was being weird. Okay. So that's part A. The other ones are really pretty similar. What was part B? Kind of exactly the same thing, only with X instead of Tor. That was part B. And the proof is exactly the same, except instead of tensor, except one of the tensors switches to a Hom because we're doing X instead of Tor. So maybe no need to even go through that. And what about part C? Part C is a little bit different because now we need S to be a projective R module. And this is probably the most important one. So this is the one that's going to give us the cohomological Shapiro's lemma, which is the one that we'll use most often. Okay, and so yeah, so we want to see it that way. So all right, so what's going on here? So since S is a projective R module, you have to think about this for a little bit, but it's pretty easy. It follows, therefore, that then if S itself is projective as an R module, then if M is any projective S module, then just regarding it as an R module in the usual manner, then it will be projective. I mean, if you don't see that, do it for free modules first, and then just come right out. Okay. And so therefore, what's the point? Therefore, is that if we take a projective resolution in the category of S modules, then by doing nothing, it's also a projective resolution in the category of R modules. And so that was one key point. And then I think we're going to use our Hom identity, and we're going to be done. So right, so X in S from M into this this Hom guy. Let's see. So right, in order to do this, I should be taking again, X is a functor of two variables. I could compute this by computing a projective resolution of the first argument or an injective resolution of the second argument. Evidently, I want to compute it by taking a projective resolution of the first argument and then Homming that projective resolution into the second guy. So we do that. And now we use our Hom identity. And that kind of collapses the S's. Telescoping Hom, I called it once and sort of like it and sort of don't. And then we get here, and then you look at this and you say, well, okay, sure. This is exactly the homology that is going to compute the X from M into N, and we're done. Okay, so I mean, this is like homological algebra working for you rather than against you. It doesn't, you're never gonna see a more straightforward, fact about Tors and X's than this. Well, maybe you will, but not very often. Okay. That completes the proof of Shapiro's lemma. And then the last thing, which I definitely said, but I really should prove, again, I think I'm probably going to have to, well, we'll see. Maybe I can slow down a little bit. Yeah, so here's the really key result. So Y is, and again, to my taste, I wish Harari had just said this out of the front of his mouth rather than the side of his mouth. He doesn't really define the actual induced module, which is used in which you tensor from ZH to ZG. He only defines the co-induced module where you Hom from ZH to ZG, and he calls that induced, which, to be fair, is not his. He's not the first person to do that, but he kind of only introduces the honestly induced module kind of in various remarks and stuff. And so I found myself in reading it, I found myself just kind of chasing through all these, almost parenthetical remarks, but like, why not you? I mean, no one of them is better than the other. They have, again, as we discussed, they both have a right to exist because one of them is the left adjoint to the restriction from G modules to H modules, and the other one is the right adjoint. I think int was the left adjoint, but again, so easy to get confused on left-right stuff. And so the reason that you don't have to worry is because when you have a finite index subgroup, or even better, when the group itself is finite, then they are, these functors are isomorphic. Okay, so you have natural isomorphisms here. So that's the important result. So in general, they're not. But if you're dealing with finite index subgroups, or for us, we're really going to care about the case where G is finite. And then we want the case where G is profinite, an inverse limit of finite groups. And then we will build our Galois cohomology or a profinite cohomology, basically just by taking direct and inverse limits accordingly. Okay. But you might as well see the proof, right? So in case I go through this kind of quickly, in my homological algebra notes that I gave a link to in the Discord or whatever, Google my name, homological algebra, you'll find it, no problem. This is proved in full detail. I think I found it from my friend Ramyar Sharafi's notes on Galois cohomology. So okay. We just have to define G homomorphisms back and forth. So the way that it works is I'm going to define a phi from the co-induction to the induction. I'm going to define a psi from the induction to the co-induction. And once you actually see what phi and psi are, it really will be visually obvious that they're mutually inverse. And so what do we have to check? We have to check that there's like a well-definedness condition that comes up, and then we have to sort of in two slightly different senses, we have to check that each of these maps is well-defined, and then we have to check that each one is actually a G module map. Okay. So how do I go from a co-induced module to an induced module when the subgroup has finite index? A co-induced module is first of all a Z module map from ZG into M, but it's not just any ZG module map. It's also on both sides are H modules, so it's H equivariant. And then to that, I'm supposed to do a tensor. And I guess maybe I should have said this before. This is our big chance to see what an induced module really is. Really what you do is you kind of vary over a system of coset representatives. Oh, note here, minor technical subtlety. These are right cosets of H and G. That's what I mean by that. That's the right thing to do, no pun intended, as you'll see. But yeah, so the way that you actually do an induced module, you should think of it as being kind of formal finite sums of group elements tensored with the original module, where the sums extend over a set of coset representatives for H and G. Okay, so that's not a completely precise statement, but I'll let you think about the fact that that's reasonable. And so, okay, this is the sort of thing that I have. And so, right, so you see that I have like a G sort of tensor, tensor something going on here. And I guess here I have a G inverse. So gosh, as G is ranging over a set of right coset representatives for H and G, presumably G inverse is ranging over a set of left coset representatives for H and G, which sounds good. Anyway, so yeah, there's the minor sort of twisty thing to get this thing correct is that there's an inverse here, and as we'll see, that's the right thing. Okay, and so I send F to, it should be a bunch of things of the form something in G, tensor something in M, ranging over a set of coset representatives. And so, well, I have this, but now I have to check that this is well defined, right? So it's like I chose coset representatives. So what if instead of G, I went to HG, right? So I changed my representative of my right coset of H and G by multiplying on the left by an element of H. Well, don't you worry, this is not going to change because we're tensoring over ZH is kind of the secret. So we do this, and then I say, no. What if you did it with HG instead of G? Well, I took the inverse, so that comes out as the inverse is in the reverse order. F is H equivariant, so I can pull the H out. And now I look at this and I say, okay, this is the diagonal action of H on this guy. So if I have an H inverse over here and an H over here, I can just pull them both out. So I pull out, well, you guys didn't see that I just spit on my screen, so that's good. All right. Excellent. Yeah, anyway, so the H and the H inverse, kill each other, and they go away, and so then so indeed we just showed that this did not depend on the choice of coset representative. Okay, then we should be checking that it's a G map. So none of this is startling, by the way. I mean, I just have to check a bunch of things. So let's check that it's a G map. So I take another element, G prime. How is G acting on these things? Again, it actually acts inside on the right. So we had our little conversation about that. It kind of has to do that in order to work out correctly. And so, okay, it's acting inside on the right. And now what am I doing here? It looks like I'm kind of multiplying by a G prime and then by a G prime inverse. Okay. Again, G prime, the quantity inverse is of course G prime inverse, which cancels out the G prime times a G inverse. Excellent. Then we have this. And you look at that and you say, okay, well, same. Again, I just checked the well-definedness as we range over coset representatives. So surely if I range over the sum of all the coset representatives, as G ranges over all the coset representatives, so does G prime. So that's all I'm saying there. So that's fine. And so yeah, so I get G prime times what I had before. So excellent. So it's actually a G map. That's my map. Capital Phi. What about capital Psi? Well, it goes in the other way. So now again, I really want to compare. I want to look at what it is for a G inverse. Every group element is the inverse of something. So I do G inverse tensor something. So BG is, now I'm actually looking at an arbitrary element of the induced module. So again, except for the fact that it'd be less weird if I wrote it without an inverse, but I certainly can. It's some element of G tensor some element of M, and so by BG is whatever element of M gives me a general element of the induced module here. And so what do I do? I'm sending this to a function from ZG to M, and so a Z module map, and so which again, as we've seen, is equivalent to just a set map from G into M. And in fact, my map is just, I kind of have one, right? So here, this B sub G, if you think about it, what else is it for every G and G? It's giving me an element of M. Hey, that's my function. Okay, so just looking at this piece of data here, this is an element of M that depends on G. So awesome, that's a function from G to M. That's the function that I'm sending it to. And now what does it mean to check well-defined? Well, again, this wasn't just any old function from ZG to M. It needed to be H invariant, H equivariant. So let's actually check that this function f is H equivariant. So if I switch G to HG, then let's see. So I have, if I do that, then this thing is equal to, again, I have a diagonal action, so I multiply on H inverse on one and then H on the other, so I can do that. That's HG, the quantity inverse, tensor H times BG. And so, right, and so you look at this and you see that, okay, therefore B of HG is H times BG. Okay. And what does that mean? If you think about what it is at the level of functions, then that's telling you that the function at HG, well, the function at HG is B of HG by definition, and by the identity that we just proved, that's H times BG, and therefore, okay, so this identity that we just proved is actually the desired H equivariance. Okay, so indeed, just this function G goes to BG, as long as I stick the inverse here, defines the map. Let's see, I still need to check that the psi is a G map, which is kind of becoming a little tedious here maybe, but this is what we do. So we take an arbitrary element, we take another G prime, we multiply by G prime. Okay, we multiply by G prime, we do the G prime, the quantity inverse thing that we've done before. Yeah, and I guess there's just a little bit of summing over here. I'm summing over G. Here I'm summing over G prime. So I'm kind of going a little fast here, but you probably get the idea. And so that's the same as summing over G of G inverse tensor B G prime. What does that mean? That means that psi of G prime of X was the function that took G to B G prime. Okay, so that was how G prime acted on my psi. Let's go back. Yeah, okay. That makes sense. And then if I do it the other way, so I would like this to be equal to G prime psi of X. What is G prime psi of X? Well, psi of X was the thing that maps G to BG. And if I hit that with G prime, again, this is the action on the co-induced guy. So you just multiply by G on the right. And so if you do that, you get the map that takes G to B G prime. Okay, great. And so we found that, therefore we found that psi is also a G module homomorphism. Okay, so all right, that's a little bit technical there or whatever. Tedious, I think is the T word I was looking for, but that's what you get. And again, if you just go back and you stare one more time at what phi and psi were. So phi took the function and mapped it to this recipe, sum over the coset representatives of G inverse times evaluate the function. What was psi? Psi was taking the cosets and then just sending it to the function that was this element here. And so, yeah, I mean, if you stop and, so if I did the phi first, right, and then I did the psi, I'd just be getting this function back, which is definitely f, so that's fine. And if I did it the other way, if I did this thing, and then let's see, so I do this thing and I send it to the function G goes to BG, and then I use that function, and then I would be sending it to sum over G inverse tensor, well, this function here, which is BG. And so yeah, no, the clearest thing of all is that phi and psi are inverses of each other. You just see that when you write them down. Okay, so yeah, so that's the proof. I found a canonical natural isomorphism from the induction to the co-induction in the case where the subgroup has finite index, and then as a corollary, which I think again Harari uses. So this certainly works in the case where the group is finite for every subgroup, and then in this case every co-induced G module is also a co-induced H module. Okay. Why? Because co-induced is the same as induced, and every induced G module, it's easier to see that every induced G module is also an induced H module. I don't know, maybe we should see why. So why is proof? Because always an induced G module is an induced H module for all subgroups H. Right, and so why is that? Well, what is an induced G module? An induced G module is something of the form ZG tensored over Z with A, right, where A is just an abelian group, Z module. Right, and so if I want, so why is this also an induced H module? So I want to get from this type of expression to a similar expression with an H here instead of a G. Well, what do I know about ZG as a ZH module?
It's a free
free?
ZH module.
Yeah, great. So ZG is isomorphic as a H module to a bunch of copies, in fact, indexed by cosets of H and G. So indexed by Z mod H of ZH. This is part of the exercise. So this was an exercise. So again, somebody should really do this exercise. And so ZG is isomorphic to that as a ZH module. And so then therefore this is isomorphic as a ZH module to the direct sum indexed by cosets of H and G of ZH tensor A. And now what should I do? Actually, wait, I think it is something. Sorry about that. My bad. There we go. Well, I should probably just distribute the tensor product over the direct sum, right? And so this is equal to which of course is isomorphic to ZH tensor, the direct sum of a bunch of copies of it. Okay. Yep. Okay. So that's what's going on. So okay. So I proved that with no restrictions on G and H whatsoever, every induced ZG module is certainly an induced ZH module. It doesn't work. So this argument doesn't. I don't think it works the same way if you do co-induced modules. But okay. Well, now we know that in particular for every finite group, or more generally for every finite index subgroup, every co-induced module is also induced. So great. All right. Any questions about that? Okay, so that's the end of our discussion of Shapiro's lemma, induction, and co-induction. We'll use them, of course. And now we move on. Okay, so the next thing, just this little proposition from Harari. You can see I'm not going to prove it. I'm telling you where it is in Harari. So if you have, again, you have a finite group, and for once it really matters. And so basically here we're saying that if your group is finite, then your group cohomology is, I don't know, continuous, I guess is the fancy way of saying it. The group cohomology of the direct limit is the direct limit of the group cohomology. Okay, so great. And yeah, so I mean, look, I just don't want to spend the entire course in chapter 1. So I won't prove it. This is a nice application of this dimension shifting business I talked about, where you embed things in co-induced modules. But it still takes some. I actually thought his proof was like a little on the brief side, but maybe someone would like to present the proof at some point. And then in lieu of making a proof, I'll make a remark here. So again, he doesn't always make it. If you just assume the group is finite all the time, then you sort of lose track of when you actually need it. And here, so this is Kenneth Brown of Cohomology of Groups, GTM fame. So for any group, you can ask whether this type of continuity result holds for all directed systems. And it turns out that that's equivalent to an interesting condition on the group, it's a finiteness condition for projective resolutions, but it's not the same as the finiteness condition we were looking at before. So we said that a group had finite, cohomological dimension if Z admitted a finite length resolution by a finite length projective resolution by Z modules. Wait, no, I'm sorry, I'm getting maybe. Yes, that's exactly what we said. So that the finiteness of the length of the resolution, that's what we called finite cohomological dimension, right? But here we're taking the other finiteness condition. The resolution could be of infinite length, but each module in the resolution should be finitely generated. Okay, and so he showed that this innocent looking continuity result is equivalent to this somewhat, anyway, this is a finiteness condition on G that you've probably never seen before. Okay, but one thing it's, I mean, at least Harari's result should be a consequence of this theorem of Brown. And if you look back at the standard resolution, right, then the standard resolution was a free resolution of Z by ZG modules, and the rank of the nth term in the standard resolution was what was it? It was like the cardinality of the cardinality of G to the n, or it was the cardinality of G to the n minus 1. It was the cardinality of G to the n. And so, of course, the cardinality of G to the n is finite if and only if G is finite. Okay, so this is a kind of weird condition to check. And how do you know whether your group admits a projective resolution by finitely generated ZG modules? Unless, I guess flipping back, the resolution that we gave for the group Z, right? I don't know, do I want to flip back to it? I kind of do. Still going. Yeah. So here our example was for an infinite cyclic group, right? And before we even defined our standard cochains and whatnot, it was just no problem to write down a free resolution of Z as a ZG module. And you see that each of these guys has rank 1. So also, I'm not saying that it only holds for finite groups. In fact, according to Brown's result, it works for the group Z as well. Okay. In general, it's a kind of weird condition. It certainly holds if the group is finite. I don't have a good sense of which. I guess it's going to quickly follow for any. I'm sure we can prove based on what I've just said that it holds for any finitely generated commutative group or whatever. Anyway, okay. So that's a result. Let's move on. The next thing I want to talk about is this kind of. There's a lot of functorialities here. So by its nature, I mean the cohomology groups are functors, right? They're the derived functors of X from Z into M over the group ring. So they're, I mean, but by their very nature, they're functorial in M. Okay, so functorial meaning covariantly functorial. So if you have a map from M to N, then that's going to induce a map on the cohomology groups in the same direction, right? So you can have cohomology maps from Hn of Gm into Hn Gm if you have map, anyway, same direction. On the other hand, it's functorial in G, but now it's contravariantly functorial in G. Okay, so that's not so surprising, but let's see why. If I have a group homomorphism from G prime to G, well, if we think of this in terms of modules over a ring, then we're pulling back, right? So that the natural functor associated to this homomorphism restriction takes us from G modules to G prime modules. So just to give a name to that, let's really call it, use the pullback notation just to give it a name, but it's the usual thing. I mean, obviously, something, if you have G acting on something and you have a homomorphism from G prime, then you let G prime act on it via the homomorphism. So nothing fancy. And you think about this for a little bit and you see that This means that the G invariants are going to be contained in the G prime invariants once you use F to regard it as a G prime module. So that's just pretty clear. So if, I mean, again, G prime is acting via this homomorphism, right? And so if something is fixed by every little g in G, then F of little g prime is going to be an element of G, so it's going to fix it. Okay, so this is also as obvious as it gets, I guess, in this sort of thing. And now I really don't want to talk to you about it. You can read this type of thing on your own, but really general homological algebraic nonsense takes this as input and gives us a morphism of cohomological delta functors. What does that mean? It means that we have a map from the cohomology groups in G, a morphism from, these are functors, so this is a natural transformation of functors. Again, the most important thing to note is its contravariance, right? So I have a map from G prime to G, and I'm pulling back by it, right? So this is a map from cohomology of the second group to cohomology of the first group. Okay, so what does the morphism of cohomological delta functors mean? That means if I wrote out all the long exact cohomology sequences, then I would get like an infinite commutative ladder of, from the one exact sequence to the other exact sequence. Okay, general nonsense. Okay, and some more just tiny little formalism here. You can do both of these things at once, and I've always found the terminology for this slightly pretentious. It's like, well, like, it couldn't be any. If you stop and think, how should you combine the functoriality in the module with the functoriality in the group? There's only one thing that you could do, and this is it. So there's nothing fancy. If I have a G prime module M prime, okay, and then I have a map here. And okay, there's some condition here, but what should really be happening? What should really be happening? Let's just kind of think about it. What should be happening here is that yeah. So this is going to be a let's see what's happening. So this is going to be a homomorph. Okay, hold on. Actually, maybe I do need to stop and think for a second. I have a homomorphism there. Did I not want to say? Yeah, I think I wanted to say also that M is a G module. Or am I getting myself confused? Let me think for a second. No, I do want to say that. Yeah, I think so. M is a G module. M prime is a G prime module. And now I have a map here, a map of Z modules satisfying this condition. But what is this condition? This condition is saying that U is a G prime module map. How am I allowed to have a G prime module map from a G module to a G prime module? Well, no problem. If you're a G module and you have a homomorphism from G prime to G, then again, by pulling back, you make it a G prime module. Okay, so there's nothing surprising is going on here. You have to kind of parse it all out. But so this is exactly the situation. I have a G module M, I have a G prime module M prime. One says a compatible pair is what is the compatible pair? I guess the U and the, anyway, this data is the data of a compatible pair, but really all it means is that U is a G prime module homomorphism. Okay, right. And then under this situation, well, again, we have G prime modules. Oh, it looks like I changed my M's to A's. Sorry about that. Let's unchange them. Okay, sorry. So yeah, so then certainly by what we just said before, we have a map from A to A prime, which is a, again, what does this compatibility condition mean? It means that if you put the induced G prime module structure on A just by pullback, then this map becomes a homomorphism of G prime modules. Great. Therefore, by what we said before, we certainly have this covariant functoriality here. And what we're saying is that we can compose this with this pullback map from G prime to G, this contravariant functoriality. And so, yeah, so overall, we get a map in this direction. So we get a map from HG into cohomology G comma A into cohomology of G prime comma A, which really means F star of A, because that's how we're regarding A as a G prime module. Yeah, okay. So I really am just combining the contravariant functoriality with respect to the group with the covariant functoriality with respect to the module. Okay. And again, the data is you want a homomorphism of like this, which satisfies this. Again, this is the only compatibility condition you would ever write down, and then you get these things. Okay. And then, by the way, like these are not mysterious at all. If you just say like, okay, by the way, like when you see a fancy definition in group cohomology, you should ask yourself, how do I compute this using cocycles? Okay. And so if you do know how to compute it using cocycles, well, that's pretty good. And then maybe, your textbook or your instructor or somebody should be explaining why the thing that you're manipulating using these explicit cocycles, why it's actually like properly functorial and all that kind of stuff, right? That's for the people who are setting up the theory to worry about the most. But the other way around is kind of worse, if I'm being honest. Like sometimes things get defined via fancy homological algebra nonsense. And then you might be in a situation where like, well, yeah, but now I actually have like a cohomology class, which is given to me by a cocycle, and then I do this operation to it. What did that do to the cocycle? You see what I'm saying? So in practice, it's arguably more important to understand how things behave on the cocycle level. But this is totally harmless. What is this at the cocycle level? Yeah, it's pull back and push forward. It's just, that's all it is. A cocycle is a map from some number of copies of G into M. If you pull back your map on G, that's what it is. If you push forward your map on M, that's what it is. So this is totally, totally innocent at the cocycle level. It's exactly what you would think. Okay. Right, and then let me give you two very important special cases of this. Very important. So for any subgroup of a group G, no conditions whatsoever, then, well, we just had a map of groups, so you pull back in the opposite direction. And this is a very important map. It's called restriction, because we're restricting to a subgroup. And again, at the cochain level, what is this map? We're taking a map from G to the N into M, and we're restricting it from G to the N to H to the N. So couldn't be more clear what this restriction map is on the cochain level, but obviously it's a very important map. Now I want to do quotients. So of course I should take a quotient by a normal subgroup, right? So if I have a normal subgroup that I'll call N, and then I have a G module, now I think I didn't quite want to assign this as an exercise, but if you want to do a really easy exercise, you should convince yourself that if you start with a G module, right? If I take G invariants, I give everything away, and then I only end up with a Z module. I've used up like all of my structure. But if I only take N invariants, then I've only used up some of my structure, and I still have something left. So the map from M to Mn, when N is a normal subgroup, again, you could think of it as Mn as just being a Z module, but it's still a G mod N module. Okay, so that's the little exercise that Mn is still a G module. It's a G module on which N acts trivially, and therefore G acts on it through the quotient G mod N, but the quotient G mod N may very well act non-trivially. Okay, so that's you pull out your pen and you see that this is true. And so where's our compatible pair? Well, what do you think? So mn into n, that's what's happening on the module side, and then the quotient map is what's happening on the group side. And it looks like I changed an M to an A again. I keep doing that. Sorry. But these are called the inflation maps. Okay. So you have these maps start from cohomology of the quotient, not of the original, not of the G module, but of its invariance under the normal subgroup into the cohomology of the group itself. Okay. Again, similarly, what is this map on the cochain level? It's exactly what you think. You're just pulling back from from Gn to G, and then you're composing forward from AN into A. It's exactly what you think. And again, as we'll see maybe later on in this lecture soon, these are very, very important maps. Okay, there's an exact sequence related. Okay, let's see. Yeah, so I'm just this is a little bit random because I'm just trying to tick off what he does in this first chapter. So now, if I have a subgroup H of G, no finiteness conditions, no normality. Again, as I mentioned, every free ZG module is again a free ZH module. That is an exercise that builds easily on a different exercise. Follows easily, just take direct sums of everything, that every projective ZG module is a projective ZH module. Well, then you could ask, what about injective, right? Is every injective ZG module also an injective ZH module? And Harari proves this. He proves it only when G is finite, but I'm pretty sure that that's just because of his standard assumption, and actually his proof is valid in general, but it's more complicated than what he could have done. And so this is what I want to say instead. I want to use some abstract nonsense in our favor. I'm not pulling abstract nonsense from anywhere. This is abstract nonsense from the appendix of Harari's book. So here it is. It is abstract nonsense. I have a functor between two abelian categories, okay, as we will. If your functor has a left adjoint, so again, that's the blab equals arb thing, just if you write whatever, you look up what adjoint functors mean. If it has a left adjoint that is itself an exact functor, then it follows that the functor itself, not its exact left adjoint, takes injective objects to injective objects. And then there's a dual statement, totally dual statement that you get surely just by reversing all the arrows. If your functor has an exact right adjoint, then dually, it takes projective objects to projective objects. Okay. So I think I haven't gone back and added this yet. I guess you guys still have a lot of exercises to do. I think this is he includes this in the appendix. He says, "Oh, this is easy," and then he cites like somebody else's like lecture notes or something. And so I don't know. It's easy to do it. So I think this is if you don't like homological algebra nonsense, you don't have to do this exercise. I won't make you, but this is actually useful sometimes. Okay, and so now I want to apply this general nonsense where we're exactly in a situation to do it, because we just found a functor that like OMG had a left adjoint and a right adjoint, right? So the left adjoint of the restriction functor, as I said before, is the induction functor, right? This was the beginning of our discussion of Shapiro's lemma, right? That was whatever. This was one of our Ham tensor stuff identities, right? And so is this exact? Not only is it exact, we've already used that it's exact in order to prove Shapiro's lemma, right? Again, for this type of thing to be exact is to say that ZG is a flat ZH module, but we just said it was free, so awesome. So yes, induction is an exact functor, and so therefore restriction, listen carefully, has an exact left adjoint. According to this general nonsense exercise, that means that restriction should preserve injective objects. Great. So therefore, the restriction of an injective G module is going to be an injective H module. Okay. This is sort of reminiscent of what I was talking about like 15 minutes ago, but it's not exactly the same. Okay. now we move on, but also our restriction functor had a right adjoint. The right adjoint was the co-induction, right? And so the Tom from ZG into blah, 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 blah. What would the conclusion of this be? The conclusion would be that if it were true that the co-induction were exact, then the conclusion would be that restricting a projective ZG module gives us a projective ZH module. Gosh, that sounds familiar. Oh yeah, the conclusion is what we already knew up here. Okay, so I guess we didn't need to say it in terms of this exact functor. It doesn't say if and only if, so, but it kind of suggests, doesn't it, that, that the co-induction is exact as well. That would give us a second explanation for this, and that's no problem. So when is, it's just, we're just doing, very, middle brow homological algebra at best. So hom m into blank, when is that exact? Again, I get light ref confused sometimes. You heard it here first. Wow, that's like, I wish that was I had said that intentionally. Yes. So ignoring the light ref confusion that you sometimes have, you look this up and you see that hom m blank being exact is a characterization of projective modules, where if you do it the other way around, hom blank m being exact is a characterization of injective modules. And of course, if you just carefully look at what injective and projective means, not just modules, in any abelian category, this exactness is the characteristic of projective. And so, all right, well, ZG is a projective ZH module. Once again, that's kind of similar to what we were trying to prove, but okay, but it's true. Okay, and so you see that. Yeah, so in my second proof that every projective ZG module is a projective ZH module, I use that ZG is a projective ZH module, and then I use some homological algebra nonsense. But anyway, I think it's satisfying to see. So why is induction and co-induction so great? Well, induction and co-induction are the left and right adjoint of the restriction functor from ZG modules into ZH modules, and they're both exact functors. That's why induction and co-induction are so great, because they have such nice properties. Okay. Any questions about that before I move on to yet another thing? Okay, so I'm going to go for a bit longer. How much more? Oh, wow. I only have one more page. Okay, I'm going to go to the end of this page. Yeah, so I really am moving quickly. Right, so as I said before, so Harari does prove that an injective ZG module is also an injective ZH module. And again, he says it for finite G. And at first, to be honest, I thought that his proof was only valid for finite groups. And I looked at it more carefully, and I'm like, no, I think I like the proof. In general, you can look, if this sort of thing is interesting to you, you can look at it. If not, I just gave you an easier proof, so you never have to think about it again. But this is I think his proof is in some ways more interesting, but it's more complicated. Okay, so here we go. Now comes the really exciting stuff. So we have an inflation restriction exact sequence. Okay, so if I have a normal subgroup H, I guess I'm calling it H now, of a group G, and then we have a G module that I guess I'm calling A. So part A, here's an exact sequence. So the H1 in the quotient of the H invariant injects via inflation into H1G, and then you have the restriction map goes from, well, it's the restriction map, so it just goes to, so this sequence is exact. I'm not saying that this map is surjective. In fact, what my finger is covering is telling you something that's telling you that it's not surjective in general, but at least you have this much of an exact sequence. So that's your kind of level 1 inflation restriction sequence, or infres sequence, as you may grow accustomed to calling it. But now part B, I'm going to tell you more. First of all, again, now you take seriously the fact that if H is a normal subgroup, then the H invariance functor isn't just going into Z modules if you don't want it to, it goes into G mod H modules, okay? And if you think about that for a second, you're like, well, okay, if that's my target category, then my cohomology groups are living in the target category of the functor. That's how it always works. And so therefore, all these cohomology groups of H are themselves still G mod H modules, right? I still have, but these were, I had a functor, it landed in the category of G mod H modules. I took some, I was in that category, I took some resolution, and then I did like a kernel mod image. Everything is happening in the category of G mod H modules here. And so sure, if you like, this cohomology group and all the higher cohomology groups just as well still have the structure of a G mod H module. And so, the point, of course, is that this H1 HA with G mod H invariance is, of course, a subgroup of if I didn't take the G mod H invariance, okay? So I have better luck with my exact sequence, extending my exact sequence, right? So by the way, like that's the point, like this really probably wasn't surjective in general because the image for sure landed inside the G mod H invariant subgroup, if you see what I'm saying. So, we really want to keep track of this extra information. And is it surjective once I do that? Well, maybe, maybe not. There's this more complicated map. Notice this map here is the one map that I'm not naming inf or res. Okay, so I'll tell you only a little bit more about this map in a second. And then, then I have this, and then I have this. Okay, and now here's okay, so this is how many terms do I have here? 1, 2, 3, 4, 5. Okay, so if anybody is like really fond of homological algebra, do you happen to know what kind of higher level homological algebra gadget will give you a 5-term exact sequence? Kind of fancy. Going twice. So this is the exact this is the 5-term exact sequence of terms of low degree coming from a certain spectral sequence. So that's the answer. So first of all, why am I stating part A and part B? Part B is just better than part A, right? And so the reason that I'm doing this is that, well, part A, you can prove only using cocycles. This is probably a good exercise too, by the way. I will list this as an exercise. So, just write everything out in terms of cocycles. I've told you what the inflation map is. I've told you what the restriction map is. It's just one cocycles, right? So this is a very good exercise. Just cocycle it out. And then I think, now I remember Harari makes a good comment that there's such a thing as non-abelian cohomology, which means that the G module is not necessarily a commutative group. If it's just a group with a G action, then you can still do some stuff. And then there's this part of the inflation restriction sequence is valid even in non-abelian cohomology. And so how do you prove that? Well, you prove it by messing around with cocycles. It turns out, though, that there's a Hauschild-Serre spectral sequence, which really is the special case of the Grothendieck spectral sequence that whenever you have a composition of two functors between nice abelian categories, there's something called the Grothendieck spectral sequence, which is a big generalization. So Hauschild and Serre came up with this spectral sequence literally for group cohomology. And it just turns out it's a special case of this more general construction. So like if you open like Weibel's homological algebra, you could ask Brian if he's going to do the Grothendieck spectral sequence in his homological algebra. Be cool if he does. Anyway, but yeah, so if you have excuse me, one of the two functors here, the two functors are, we're viewing taking G invariance as a composition of first you take H invariance, then you take G mod H invariance. Okay, so you can't argue with that. We're expressing the G invariance functor as a composition of two other invariant functors, and it turns out that's all you need. There's some Grothendieck spectral sequence, and I'm really not going to talk about what that spectral sequence is, but a spectral sequence gives you the edge maps from the spectral sequence, give you an exact sequence of terms of low degree, and that gives you a better a longer inflation restriction sequence, which again is really useful. I'm thinking of a paper of mine in Galois cohomology where I used this, somewhat longer inflation restriction. So this unnamed map, well, it has a name. It's called transgression. It looks like the hardest one. It's some kind of co-boundary, map and blah, 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 blah. And so, yeah, unfortunately, I'm not telling you what it is right now. In order to figure out what this map is, you have to kind of look at what the recipe is for getting this 5-term exact sequence from a spectral sequence. And so, look, it's not only, don't be too scared. If you really needed to figure out what this map is, you could figure out the map. Okay. And again, this longer, the short one is useful is for sure. And sometimes it's useful to have the longer one. But yeah, having if you're computing anything in Galois cohomology, like this is your number one tool, like for sure, this inflation restriction exact sequence. Okay. All right, I just need to get to the end of the page. Oh yeah, so now there's this thing called co-restriction, which I'm going to give an inadequate treatment of right now because I want to move on with things. So so for any subgroup, I define this restriction map. No problem. Now, if the subgroup has finite index, so again, always when the group is finite, which is starting in the next lecture is going to be the case that we care about. If you have a finite index subgroup, it turns out that there's a functor in the opposite direction, therefore called co-restriction. Okay, so it goes from, it's sort of pumping you back up from cohomology with respect to the finite index subgroup to cohomology in the entire thing. Okay, so that's called co-restriction. And I'll tell you one really important property. So if the subgroup has finite index, call it n. Well, you can compose these maps. And I'll tell you what happens when if you restrict and then you co-restrict. What do you get? Then you get a map from H star GM back to itself because restriction goes to H and co-restriction goes back to G. And it turns out that restriction followed by co-restriction is multiplication by the index of the subgroup. Okay. And that's super important, believe it or not. I think, in fact, I mentioned this like almost a year ago at this point. When we do get to Galois cohomology, for any Galois cohomology class, n greater than or equal to 1, I will define two positive integer invariants, its period and its index. And I will tell you that the period divides the index and that they have the same prime divisors. And the reason for why the period divides the index in Galois cohomology, once you get to that point, the proof will be, recall that if you restrict and then you co-restrict, then you get multiplication by n. So that's certainly very important. And so at the moment, I'm only going to tell you what co-restriction is on level 0, okay, on the 0th cohomology groups. And I just hinted, the actual definition of co-restriction only explicitly tells you what it is on the 0th cohomology group, and then does some real, homological sneaky tricks in order to extend. So some effaceable functor is being extended from n equals 0 to all n. And again, just to keep track of the point that I told you before, like you can read about that. You should read about it. But in the back of your mind, you should be like, wait, so I defined a functor co-restriction in terms of like effaceability and universal properties of homological delta functors. Hey, how do I compute this co-restriction map? The definition didn't tell me what it was, on cocycles. And, hold that in your mind, maybe later we'll need to compute a co-restriction at the cocycle level. And, we'll see whether we answer the question, but hold that question in your mind. Right? So what I'm trying to say is that the general nonsense definition of co-restriction is actually not. It's only the beginning of the story, because in practice you often will want to do a co-restriction. Anyway, so at level 0, it's a very familiar map. It's sometimes called the trace. It's sometimes called the norm. We'll see in specific instances. We will see that in one situation, there is a setting in which the co-restriction at n equals 0 is literally the trace map from field theory. And we'll see a situation in which the co-restriction at n equals 0 is literally the norm map from field theory. Okay, so it's a very reasonable map. So what is it though? Well, again, at n equals 0, I'm trying to go from the H invariance to the G invariance. And if you think about it, if H is a subgroup of G, being G invariant is a stronger statement than being H invariant. So the G invariants are a subgroup of the H invariants. And I'm trying to go back the other way. But then you think about this and you're like, oh, I know, it's the same usual trick. If you want something to be invariant under the action of a group and it isn't, you average over it. Okay? That's the great trick. It's like the most times when you make something invariant, you're averaging over it. If your group is finite, then what is an average? Well, maybe it's just a sum. If your group is infinite, oh, maybe use an integral. But still, right? And so here we have a finite index subgroup. That's what I'm telling you. And so therefore, what is this map? It's the most reasonable thing it is. You range over a system of coset representatives, left coset representatives for G and H, and you hit it with those coset representatives. Is this well defined? Of course it's well defined because you're starting with the H invariance. So to say that something is H invariant precisely means that when you hit it with an element of G, the way that G acts on it, it only depends upon the coset. Okay, so it's immediately clear that this map applied to the H invariance is well defined. And in case you've never seen something, I mean, try it. I think you'll find that this is actually G invariant because we summed over the action of G. Okay, so at the n equals 0 level, the co-restriction is like, well, things are looking additive here. So this is looking like a trace. But if I was like, no, actually the group law on M is written multiplicatively, and they'd be like, oh, my mistake, it looks like a norm. Okay, so that's what, anyway, so more about this later. We'll see more about it later. But again, through a kind of cohomological trickery, the co-restriction gets defined also for higher n. I encourage you to read about that. As a nice application of dimension shifting, you should read the proof that this identity is true on all the cohomology groups. Again, restriction followed by co-restriction is multiplication by the index. The general nonsense definition, the abstract nonsense definition of co-restriction allows you to prove that identity. And so that's a good thing for you to read about. But again, keep in the back of your mind, how do I actually compute the co-restriction? And we'll see later if that comes up. Okay, that's all I wanted to say for today. Tomorrow I want to start chapter 2. Any questions? All right, well, on to something different next time. So see ya.
See ya.